We really appreciate the opportunity to be here today and talk with you both in the crowd, and we have a number of folks on Facebook. This is the first time we've done that, so people are reaching out digitally as well. Today, as mentioned, we're going to go over the results of a very long 5-year study that was funded by you and me as citizens of Memphis and Shelby County in order to better understand our aquifer system. So the plan is that we're going to go through the presentation. It should go relatively quick, takes about 40-45 minutes. It's like watching a movie. And then at the end, we will sit up front and answer any questions that you have. Before getting started, if my CAESER staff could raise their hand around the room, then these are the folks in the back and in the front and on the side that have contributed greatly to the study that we have done, and appreciate them enormously for this. So, beginning, project overview. This was a large-scale study to determine the location and impact of naturally occurring breaches in the upper protective clay layer to our drinking water aquifer. The project actually conducted 22 individual investigations. And being a university, we're all about students, right? So it was master's students and doctoral students doing it as part of their graduate study, and that those results were provided to MLGW for their consideration and implementation. So you've heard this kind of topic of a hole in the clay layer or a breach. So what is a breach? A breach is a pathway in the protective clay over our drinking water supply that allows water from a shallower system that's unprotected and known to be contaminated in certain locations to bypass the protective nature of the clay and get into our drinking water supply. So why should we be concerned? As mentioned, Memphis is heavily urbanized, and because of that, there is a greater threat of contamination. Therefore, if these breaches exist, it could bypass the protective nature of the clay and get in. As was mentioned, it is the best drinking water, right? I mean, when you leave town and you go drink water somewhere else, you can't wait to get back to Memphis. It's just really great water, and the breaches actually threaten the quality of that water. Therefore, studying their presence and the impact that they have on the Memphis aquifer, which is our primary drinking water source, was very important. So when we talk about breaches, we look at them in two different ways. This is kind of a definition that we came up with at CAESER. There's a suspected breach and a known breach. A suspected breach is identified using a number of methodologies. Could be an anomalous water table depression, could be geochemistry, age dating, it could be just mapping the subsurface, computer modeling. We're going to go through some of these, but to get off the list of a suspected breach and to be known as a breach, you have to drill through it. By drilling through an actual breach as an eyes on, you can actually go right through, you do not see any clay. That is the way you become a known breach. And the way you do that is drilling, as mentioned. The type of drilling that we do typically is called rotosonic. Whoa, what did I do? Is rotosonic. And what's really nice about this particular drilling method is that it, as it goes down through the soil, it actually tells you exactly what you're going through the topsoil, through the material that creates the shallow aquifer, the protective clay, and then eventually down into the Memphis aquifer. It's a really great tool. It gives you an eyes-on approach. However, when you kind of kick it back some, it only gives you a pinpoint piece of information. Drilling only gives us a point location. And the rest of the area you can't see unless you drill. Where rotosonic drilling costs $30,000 a pop. That's pretty expensive. So if you want to do a broad area, if you want to go from here to the University of Memphis, that's a lot of drilling. That's $30,000 every time you punch a hole. So what we do is we do something called geophysics. And geophysics allows us to see underground in a very continuous, detailed way. And therefore, what you see that little red, purple area? That's a breach. And what's real interesting is that those breaches is no longer just the fact that there's a breach, that now they're connected by paleochannels. And it's a new little term that we've been bringing up. So what is a paleochannel? The way to think about that is how the clay was first deposited, that protective clay. In the ancient ocean, where we stand right now used to be a sea, and the water was very still. The fines in the sea would settle down and build that clay layer. Once that clay layer was built, the water would go away, and what would be deposited next were by rivers. And therefore, those rivers would actually eat down into that clay, creating a channel, like an erosional scar. Well, sometimes it ate down deep enough and created a breach. So it's not just a breach, it's the fact that there are channels that connect them together. Well, once that was filled, more sediment collected on top and actually buried them. It buried the channels and it buried the breaches. And therefore, these things are hard to find. They're underground. There's no representation of them at the surface. So we have to go find them. So what we did is we flew northern Shelby County. What you see here is a bunch of greens and yellows. And wait for it. You'll see some dotted lines. Those dotted lines are the paleochannels. This is very important. This was an important, let me go back. This was northern Shelby County. This was aerial electromagnetic survey done by the USGS that we contracted them to do. And what it does is it gives you a picture beneath the subsurface that's more continuous than drilling. And we only could fly in the northern part of Shelby County because it was rural. You cannot fly this device over homes. So unfortunately, we cannot fly it over the lower 2/3 of Shelby County. But these little hotspot areas of pinks and whites, those are breaches. So it's no longer that there's just a breach. The breaches are now connected through channels, and that's impactful. Just for reference, those are Lusahatchee River. So how do we go about finding them? Geophysics is one way that you just saw. Another way is looking at the chemistry of the water. The chemistry of the water is like the ingredients for baking a cake. The Memphis Aquifer has its certain ingredients. So we can go to a well that's pulling water out of the aquifer, take a sample, send it to the lab, and what we get back are constituents that tell us the ingredients of the Memphis Aquifer water. But sometimes we take a sample of water and there's something else in there. It's not just what we thought was in the Memphis Aquifer. There's other water in the system. So when we go and send that to a lab, we get back different numbers, the numbers in red. So this difference in chemistry tells us that there has to be a breach nearby. The Memphis Aquifer should be protected by clay. Nothing can get through. But if other chemical type water is getting in, it can only get through a breach. So our thing is to go find it. So we have our water, we have it in the aquifer, and we go and try to find where it could be. What we're going to find is that some water is in the stream and some water is in the shallow aquifer. So that is telling us that those waters are actually getting put through a breach somewhere. So the water is coming from those two different locations, and therefore they must be going through an actual breach. Now the thing is about geochemistry, it says that yes, the only way for this water to get in is through a breach, but it does not tell us where. It does not tell us where the breach is located. So we still have to go find it. This is why we call it a suspected breach. You just know that it's somewhere nearby. As part of this study, we investigated 5 of the 10 MLGW well fields for chemistry. The larger ones are the larger hexagons, and these are the 5 we checked. Davis, southwest Memphis, Mallory downtown, Sheehan by the University of Memphis, McCord is by Bartlett, and Shaw is out in East Shelby County. Look at the dates. You have age and mixing. So the Memphis Aquifer is meant to be, or supposed to be, 2,000 to 3,000 years old. Look what we see. Look at Sheehan right there in the middle, 18 to 60 years old. That means that young water is getting in somehow, some way. It's supposed to be 2,000 years old, but look at Mallory downtown. Isn't that interesting? 2,000 years old, no mixing. Do y'all know what that means? Mallory is pulling in 100% Memphis Aquifer water long ago, 2,000-year-old water, nothing else. But the other well fields are showing water coming in. In fact, we did some earlier studies prior to this one at Allen and Lichterman, and they're also showing young water getting in. What this means is, look at McCord. See, it says 67% mixing. What that means is that you go to a well and you take a sample in your cup, and at that well, 67% of the water is not Memphis Aquifer water. It's coming from somewhere else, okay? What we want the water to do is look like Mallory. So another way of getting at where a suspected breach is drilling. Now, I mentioned that was expensive. Well, these wells were put in long ago, so we can go back to these old records when they were drilled and pull those up. And we can actually load that data, those wells, into the system and map out what the subsurface starts to look like. And they just come up as a bunch of little squiggles. And these go at various depths. In this example, the deepest one over here is 360 feet. To kind of put that into perspective, that is 13 school buses deep. So the Memphis Aquifer is about 22 to 25 school buses thick. That's 2 Clark Towers standing on top of each other. So our geology is like a stack of pancakes. And therefore, we can follow these little squiggles across and connect them together. And it's going to start to tell us a picture of what the subsurface looks like. And we know from some drilling what that should be with the clay and the Memphis sand. And then we can connect all that together, and all of a sudden we get a picture of what the subsurface looks like from these old logs. And in some very rare cases, sure enough, one of the drills went through a breach. So this is pretty good, but what we have here is a map showing where we have these drill sites. You can see some of them are really clustered together, some of them are really scattered. Look at North Shelby County. Pretty scattered, huh? Now, that would be bad. However, guess what? That's where we flew the AEM survey. So it's pretty detailed. So now we're looking at the lower 2/3. And what we see is that when there are clusters, there's a lot of wells nearby, so we can actually get a good picture of what the subsurface looks like. But everywhere else is a bit challenging because it's so scattered, it's hard for us to really draw a detailed representation of what the subsurface looks like. So we're very limited if you look at the map in being able to draw these cross sections. However, where they are very detailed, we are able to produce extremely powerful, using a very powerful software package, very detailed cross sections in 3D that we can actually move around and manipulate and see where breaches could be or thinning of the clay. Another way at getting at trying to find a breach, again, we're still into the topic of suspected breaches, is groundwater surface water interactions. On the left, you see normal. On the right, you see abnormal conditions. The thing that's similar between them is the winter conditions, the black dotted line. When the water's really high because it's raining, which is about to start happening pretty soon, we're entering into our wet season, the rivers are going to run high and they're going to push water into the aquifer. But in the summer, it's interesting. The normal condition on the left, when it's summertime, you're driving down the road and you cross the Wolf River or Loosahatchee, hasn't been raining for 2 days, the flowers in your garden are kind of, leaning over, water's flowing in the rivers. Why is that? Because the aquifer is feeding, the blue is feeding the rivers. That's shallow aquifer giving water to the rivers and making them flow. But on the right, what happens is when there's a breach nearby, the rivers actually lose water locally and go through a breach. So if we can find where rivers lose water, that means there's probably a breach nearby. So we looked into that, and we looked to see where some possible breaches could be nearby a stream, and then to characterize how that water moves through them. So looking at nearby breaches, we did find 2 locations. One of them is at Austin P near or on the Wolf River. At this location, we wanted to drill, but we were unable to. So we could not get the drill close enough to the site where we wanted to be. So we could not do that. But the other one was near Germantown, near Lansdowne Park. We were able to drill, but at that particular location, we hit clay. This is why we drill, right? The river information suggested there was a breach, but now when we drill, we see there's not at that location. But we started taking water levels, and what we are seeing is that somewhere nearby there has to be a breach based upon how the water's exchanging or moving up and down. So there's something nearby. So we also need to look at how the rivers exchange water. How does the water get into or out of the river? So we did some surveys like that. One of them was characterizing the riverbed. And we did this on the Loosahatchee, Wolf River, and Nankana Creek at all the sites that you can see. We implemented instrumentation in the rivers. And what we found were about 20 sites that had high flow, 79 to 620 feet per day. Put that in perspective. The speed of water through the Memphis Aquifer is 0.1 feet per day. So that's pretty fast, leaving out of the streams. But 6 sites, the little turtle with the blue hoopy thing, slow, 3 feet to 36 feet per day. And look where it mainly occurred, Nankana Creek. Very interestingly, when we went to Nankana Creek, about 3 feet below the stream bed, there's clay. Now, it's not the protective clay that protects our drinking water. It's just a shallow clay. But for some strange reason, it's underneath all of Nankana Creek except one location. And that is right there. So we zoomed in, did some more studies, and you'll see these big blue circles. That means water loss. This is during the summer, water's leaving the stream, getting into the aquifer. It's like, why is that occurring right there? Well, we went back and looked at some historical records, and someone put in a borrow pit. They were digging out sand or gravel for something, don't know what. They ate through the clay, dug through it, and now there's a connection. You know, there's a lot of irony in the world. Remember that topic I talked about, Paleo Channel? Would you not believe that there's a Paleo Channel that runs right here, goes northwest, up through Sheehan Wellfield to the Wolf River? So water actually leaks here, goes into a Paleo Channel, and heads towards Sheehan Wellfield where there are breaches. Irony. Of all the places to put a borrow pit, right? So at our last public forum 4 years ago, and we kept being asked this a lot of times, can you fill a breach? And I kept saying, no, you can't, no, you can't. Or no, I don't know what I said, but I kept saying no. So eventually I said, yes, let's see if we can figure it out. So we had a study where we did some work in the lab to see if we really could fill a breach. So when you look at the amount of water flow through a breach, what's going through the clay is pretty slow, 0.0056. But when you look at what's going through the breach, look at that. Much bigger number, 10,000 times more through the breach. So we did some lab analyses, and what we did is we built a bentonite slurry, like clay, like a syrup or a Slurpee. And we squirted into in between the grains of sand, the void space, to fill it in. Water can't get through, right? And then we used modeling to estimate that at 15 feet thick, and we reduced the flow. It went from 14.3 to 0.16. It's pretty good, but it's not great. You can still see how more protective the natural clay is. And that number, the 0.056, is a high number. You can go to other areas in the clay and get even slower water. So that's what's really different between what we have in the clay and what's going through a breach. So to answer the question, can you fill a breach? Not really. You can reduce the water through it slightly. It'll never be like the clay that's natural. And the fact that these things are paleo channeled, connected, like a web, and the fact that there is private property that you have to get access to, the likelihood is like, no, you cannot fill a breach. Sorry. Another way of getting at suspected breaches is modeling. There is a lot that goes into a computer model because there's a lot that goes into what really impacts the groundwater system naturally. And there's so much that goes on, we can't figure that out in our head. We can't put all those things together and see how it all interplays. So we have to use computer models to do that. When we walked into this study, we had a computer model that we built called CAESER 1, and it ran between 2005 and 2016. So when this particular study that everyone in this room and on Facebook helped pay for, we extended that model. And the reason that we did, especially backward, is that we think that one of the threats to our groundwater system is not just the presence of the breaches, but the possibility of contaminated water getting in from legacy contamination. These are practices back in the 1950s, 60s, and 70s, prior to the Clean Water Act, prior to the Safe Drinking Water Act, that companies had no regulation, maybe didn't even think it was bad, and they would just dump the waste out the back into an unlined pit. So we needed to take the model backwards to 1960 so that we could actually carry that contaminant from the 1960s forward to, it says up here, 2021, which is part of the study. CAESER has continued to keep that model updated every year, so it's actually updated to 2023. But this is how we carry forward contaminants. So why are models helpful? I mentioned one reason why. And one thing to make sure the models are accurate or that they give good data in equals good data out, right? So one, we did accurate pumping. We did monthly pumping of every single well in Shelby County back to 1960. We found all the historic records. You can thank Memphis Light, Gas, and Water. You can thank Bartlett, Carville, Germantown, Millington, Industries for having all that data in those boxes that someone said, they held on to it, thank you. And we got it all, and we put it into the system, and thank goodness it was there. So we actually have a very accurate model. We have improved measures of how water moves through the system called hydraulic conductivity and storage. That will be in that little pamphlet that you got. Breach conductivity, how the water moves through the breach. We never knew. It was a guess. We actually drilled through one. We drilled straight through one. We grabbed the sand. We ran to the lab. We put it in the machine and got a conductivity out of it. Now we got a good value. We didn't really run to the lab, but it kind of gives some excitement. We also added some new breaches to Sheehan Wellfield, which we'll talk a little bit about. And I mentioned the importance of rivers and the interaction with the aquifer, looking at how the river stages and how the waters between the two interacted. So what are some of the outcomes? Well, one of the things we did is we were able to test 3 different objectives. The Memphis aquifer is really thick, right? Remember I said it's 2 Clark Towers standing on top of each other, or about 25-ish school buses thick. What we see is that young water or contamination tend to sit in the upper part of the aquifer, not the deeper. So we have wells in both locations. And what if instead of having a well in the upper part, we put one way down at the bottom? Maybe we could prevent contamination from getting to the wells. This actual system ran to 2050, to the year 2050, looking to see that we could avoid any level of contamination. Another question is, let's say you do this. What if you pull a well at the bottom? Maybe you pump from the bottom, maybe it might pull all the contaminants down. We check that too. Seasonality, we're getting into our winter season. We don't wash our cars as much, we don't fill up the pool, we don't water the yard, we use less water. So maybe instead of pumping from the shallow aquifers, from the shallow part or the shallow wells, we pump from the deep. Maybe that would prevent any contaminated water from moving further toward a well, so it protects your well and it saves your well field. It extends the life of your well field. And as all things do, just like our cars, they fall apart, well, so do wells. So we have to put in new ones. So now we can also tell where to put new wells. And from this computer modeling, we can tell, this is Sheehan Wellfield in the black. The little circles are wells. The gray blobs are breaches. And the red is where you don't want to put a well. This is again to the year 2050. But the green is where if MLGW needed to put in a new well, we can tell them where and how deep. The number of models that were used to develop this was 100,000 models. They ran on a supercomputer. So, another way is modeling gives us an idea of contamination. Now, when we think about contamination, we just kind of think of contamination just kind of riding along with the water. But that is not necessarily the case. Contaminants move in a different way. It's kind of like putting food coloring in your bathtub. They spread out. So some moves with the water, but the rest of it spreads out and creates a type of plume. There are different factors that can influence this. Our aquifer, the Memphis aquifer, has iron in it, and there are some organics in the sand, and that can hold that contaminant back. That's good, it slows it down, right? Or traps it. Spreading increases with distance. The factor that says, I'm going to spread this much or that much, the farther away you go, the bigger that number gets. Microbes consume or contaminants. Now we understand this as part of the study. We did not actually investigate that, but we do know that microbes can consume contaminants. Now that's a good thing too, because it eats it away. And as I mentioned before, remember we drilled through the breach and we ran to the lab to get it tested? Getting how that works, how those breaches truly work, that's very important in a model. So the better we can get it, the more accurate information we can get on that, the better. So let's go back to Sheehan. We built a model of Sheehan well field. Again, the black box is the Sheehan well field. The dots are wells with the numbers and then some cross lines. So we ran a model, and the red are known breaches. What is a known breach? We drilled through it, or someone did. And the green is a suspected breach. So we did two things. One, we asked the model to tell us information, but then we also take a sample and send it to the lab to get us ages. So we run the model and we get 3 plumes moving toward the center. This is not real. There's not contaminant plumes moving toward the center of Sheehan. It's just a simulation of what's going on, that it moves stuff toward the well field. I will make a point that this right here is a Superfund site. It is known. And what we get is when we go to the lab, we get young water, 16.6 years, 28.3 years. So yes, the lab is telling us there should be young water getting in. Well, it has to come from those breaches. And the model tells us about mixing. So sure enough, it says you're mixing. Okay, so now we have 2 corroborating things: ages, lab, mixing, model. That's good. However, at these 2 locations, labs tell us that there's young water. The model says, no, there's nothing getting in. So what's up with that? So we notice this particular well down here, K99, has some thinning of the clay, possibly a channel, right? Yes, okay. I got corroboration by Dan. He's the man behind the curtain. So, so we went to Audubon Park and ran one of those geophysical surveys, kind of like the airplane, but this one's on land. We did it at the golf course. Thanks City of Memphis for giving us that access. We did it at nighttime, so we did not disrupt any of the golfers. And we ran a survey using electric resistivity, and what you see is this protective clay here and here, and guess what? There's that paleo channel. Ate right through it. Okay? Not only did it create a channel, it ate right through it. Now, we still call that a suspected breach. I mean, you may look at that and be like, dude, that's a breach. But you know what? The only way you get on that list is if you drill through it. Interestingly, when we include that in the model, guess what? The model now says there's mixing. Now it starts to corroborate. The last piece at Sheehan is down here at the bottom. Again, lab says 50 years. Model says nada. So there must be a breach to the south. Remember Nonconna Creek? Someone dug a hole, ate through the clay, paleo channel, up through Sheehan. Guess what? Goes right up through here. So there's got to be a breach to the south, and it's going to be running through that channel. Another way for looking at breaches is water table. In a normal case, when you're pumping, you'll get a depression and the water goes toward that looking like a funnel. But we don't pump from the shallow aquifer. So if we did a water table study looking just at the shallow, we don't pump, we will not see this. But we see depressions. We see things like this. How is that possible? It's because water is leaving from the shallow and going down into the Memphis and creates a depression. So we can use these in order to look at where possible breaches could be. We ran this in 2020. We find one at South Parkway and Elvis Presley Boulevard. We substantiated one near the University of Memphis. We substantiated another near Lichterman Wellfield in Hickory Hill area by Winchester and South Perkins. And then we substantiated another one over at near McCord, near Bartlett, at Highway 64 in Appling. So again, only suspected until you drill through it. So again, the only way you know that you are a breach, you can be claimed in that list, is if you drill through it. So when we walked into this study, this was back in 2018, before the study began, we knew that there were 2 known breaches and 7 suspected breaches. That's what we knew. This is Shelby County. This little green hatched area is where the clay is just gone. That's the recharge zone. That's where rainfall there and Fayette County fall to the ground and replenishes our drinking water supply. But this is what we walked in. At the end of the study, we had identified 6 known breaches and 35 suspected breaches. That's a big difference. And of that 35, 23 of them were up in North Shelby County where we flew that airplane, the Aerial Electromagnetic Survey, which was very detailed. And there was nothing about the geology in the upper 1/3 of the county that should suggest any difference in the lower 2/3 of the county. Meaning that if that highly detailed survey could be flown across the lower 2/3, which it can't be, we probably are looking at about 70 plus, maybe 90 suspected breaches. So as I mentioned before, it's not just a breach here or a breach there anymore, it's like Swiss cheese. And it's not just the breaches anymore, it's the channels that connect them. So it's like a spider web. So it's a lot more critical than what we had imagined before. So what are some things that we can do? Certainly, all this information was provided to MLGW. They are using their data for their purposes. What can we do as citizens or the community? One way, if there's an alternate source of water to the Memphis aquifer, use it. Industries use a lot of water. That's okay. But usually they'll take the water, they'll use it once, and then they'll discharge it and it's gone. What if they actually recycle the water? And if you're in Mill in East Tennessee, you're typically pulling surface water or water out of a cave. So if you use it again and again, it starts to scale your utilities. But here, the water is so great, you can use it upwards of probably 10 times, again and again and again and again. So industries reusing water would help us conserve water. Another one is if you are near the Mississippi River and you don't really require the high quality Memphis water, or you have the money to clean shallow water, don't use the water of the Memphis aquifer, which is great quality, pull from the shallow and let the Mississippi River give water to the shallow aquifer to give you the water that you need. Now the Mississippi River, when we picture it in our head, is brown, sediment, muddy, but that all gets filtered out by the sands and gravels of the shallow aquifer. Another alternate source of water is Mother Nature. Now folks, this is my pet peeve slide. I tell you what, it drives me crazy driving down the road and water is going off of someone's yard who's, they're watching TV, and you got 2,000-year-old water spilling into the gutter and going away. 2,000-year-old water going down the street. Or, isn't it even better when Mother Nature is raining and you're still sprinkling? Now that's just crazy. I think that the people, who do this should be the first people to make a difference, right? And maybe the second people to make a difference, instead of us driving by, is when we go past a place where that's happening, pull up the company on your phone, call them up and say, y'all need to fix that. So another way is to capture water. These are rain barrels. This allows you to get water before it just, when we build, I'm an engineer, so when we build homes, we grade away from the home. We try to get all the water away from the home and to the curb and off and gone. So we really try to move it away. But if we capture the rain, we can actually use it for maybe watering our lawn. Now this isn't going to pressurize water and put water in your second story shower, but you can water the yard with that. Maybe we should be doing that. Another one is more of the protection about contamination, throwing stuff away as in the proper disposal units. There are these around the county. However, maybe they're not available to all citizens. Maybe it is something like, well, I want to throw it away, but that's not till next month, or it's too far away. I'm just going to throw it in my can because it's right here. We don't, maybe what we ought to be doing is having a mobile system drive around and do that. Or if we have trash cans that can handle recyclable waste, maybe we could have a purple trash can to handle chemical waste. I don't know. Something better to capture all that. In our home, if you've ever been part of our Wow-mobile, you'll see this. These are things you can do in your home. From fixing leaky faucets, turning off the water when you brush your teeth, turning off the rinse water, do shorter showers. I mentioned before the 1960s, legacy contamination. When we walked into this project, the one we're talking about, we kind of had this feeling of there's more breaches out there than what we suspect. Sure enough, way more. Well, we're walking into the second part of this study, and we have this thought of there is contamination possibly heading our way. It just hasn't reached our wells yet. What happened was in the 1960s, a company would dump contaminant out the back door into an unlined pit. And over time, it would slowly move through the system and move through the aquifer up until the point to current day. But look at that, it never hit the well. The well's off to the left. And the only way we know that the water is contaminated is when we pull it up at a well. Well, by then it's too late, right? And look at all this. This is not yet contaminated. It may take another 20 or so years before it finally reaches the well. So what can we do? Wouldn't it be better if we didn't contaminate the rest of the aquifer and we could catch it before it actually reaches our production wells? One way of doing that is to look at private wells. And there's some private wells in the area, and this is where a partnership with the Shelby County Health Department is invaluable, because they manage the private wells and they monitor those private wells. And what we could do is work with them in that monitoring to where maybe we could actually sample and find the contaminant before it moves further through the system. Not only are you helping the citizen who may get hit, but you've also saved the aquifer and you save the production well, and you're able to take action more quickly. However, again, the clustering is the wells that we can actually sample. See how they're all put together, minus just a few? We don't have enough. But Shelby County Health Department and the private wells that are out there can begin to fill in where those question marks are, and we can catch stuff in between. That's what we need to be doing. So, Mr. McGowan mentioned a second study. We have started that. Here are some of the things we're looking at. One is taking that idea of breaches in the upper third of Shelby County and seeing what that might look like in the lower 2/3, just projecting that down. What would that really mean? What would it really mean if there were 70 to 90 breaches across Shelby County? What would that look like? What impact would that give? Another one is doing a parcel by parcel hotspot, going property by property by property, going back to historic records into the 1950s and 60s, seeing what was there in the distant past that may not be there anymore that could have been a contaminant source, and then find those and then run a computer model and see where it's headed and how far along it is. Then look at, when we talk about ages of water, we say, oh, this, here we have 13-year-old water, supposed to be 3,000-year-old water. That 13-year-old water is not just in the Memphis Aquifer. It has to go up through a breach, up through the shallow aquifer, up to the ground. We don't know what that is. We don't know what that time of travel is, so we need to figure that out. Remember we did 5 well fields, and then 2 prior to that, Allen and Lichterman? Well, there's some more well fields. We want to look at Morton, and then we want to look at Allen Wellfield again. The shallow aquifer is unprotected. That's the one above the Memphis. It sits above the clay. It's unprotected. There's no clay above it. It's more prone to contamination. It feeds the Memphis Aquifer through the breaches. So it is very important that we start focusing some effort on the shallow aquifer and what it's doing and how it's interacting with the Memphis Aquifer and contributing water. We mentioned the suspected breaches. We got 35 of them. We'd love to be sure that they're there or not, and the only way to do that is to drill. So we need to drill through those suspected breaches. As I mentioned before, a lot of those are on private land. So we need the citizens' help who own the land to consider allowing us on the property to drill a hole. We drill a hole, we fill it in, we put back the grass and walk away. That's what we need. And MLGW can be invaluable in helping get access as well. The aerial electromagnetic survey that was flown in the northern part of Shelby County cannot be flown over the lower 2/3. We have homes and it's just not allowed. So what we are going to look to do is do urban geophysics. It's taking that kind of airplane model and actually run that through the streets or run that through easements, the power line easements, the gas line easements. If you're driving down Sam Cooper Boulevard and you see a grass strip, run it on that. If you got a golf course, run it on that. Anywhere you got an open space, run it. We may not hit a breach, we may hit a breach, but guess what we probably will hit is a paleo channel. Because now it's not just the breaches, it's also the channels that connect them. And the USGS, the U.S. Geological Survey, has some amazing instrumentation that we're going to look at using with them. CAESER 2 model, we got to move it to CAESER 3. There are some new data, there's some new techniques of modeling. Interestingly, when I talk about the Memphis sand, and I say it's 750 feet thick, 2 Clark Towers tall, you might imagine a big old thing of sand, like a giant sandbox of just sand. Interestingly, in the upper part of the aquifer, right below you, about the upper 1/3, right there's a little thing of clay called the Zilpha clay. Down south, as you go into Mississippi, it's really substantial. And we only thought it kind of came into Shelby County, but when we start looking at well logs, we keep seeing it again and again and again. Just maybe that clay is more substantial than what we think. Just maybe that clay extends farther, because it's more substantial in Mississippi, farther north into Shelby County, and may be of some integrity that we could drop wells just below that and capture the protection of a clay that exists within the Memphis Aquifer. So we're going to be checking on that. There's a lot, and the model's really helpful for that. There's a lot more that we're going to be doing in this as we develop. So in the room, some of the new students on the project, raise your hand. Don't be shy. These are all brand new PhD students from all over the world that have come here to start their studies. This is only the first cohort. Come spring, we'll hire an equal number. We'll have about 20 people working on this again. The cool thing about PhD students is that instead of here for 2 years, they're here for 4 years, and they typically do 2 to 3 projects instead of just one, like a master's student. So You get a lot more out of a PhD, and we're glad they're here. So that concludes our presentation. We're glad that you came.